Hello and welcome to another episode of the Clojure Pills screencast. This is episode number 16 and we're going to talk about reduce. As usual, before we start, a quick mention of the book I'm writing for Money called the Clojure Standard Library, an annotated guide. The content of this screencast is roughly based on the content of the book, so if you enjoy the screencast you might very well enjoy the book. There's a 42% discount code at checkout that is displayed on this slide. If you go at the website displayed below, or if you Google for the title of the book, and if you buy the book you will have the discount code. And at reborg is my Twitter handle if you have any question, if you want to get in touch. So reduce. Reduce is a quite important functional construct, not just in Clojure, but in many other languages. The docstring for reduce is focusing mainly on the constraint or the contract with the function f that is usually of 2 arguments, but in the case of Clojure it's got a specific no arguments requirement as well. But before we go into the details of the contract, I just want to try to explain why reduce is a functional construct. It is a general functional construct, and what is representing. So I have an example, a quick example here. I have a Fibonacci sequence function that, given a number n, is returning the nth element of the Fibonacci sequence. So if we evaluate this, we do Fibo of 10, for example, is returning 55. And Fibonacci sequence is the sequence of the numbers where each number is the sum of the previous 2. This version of the Fibo function, it's quite elegant. It reads almost like the English language. So we have a 0 case, we have a 1 case that are specific, and then we go into the iteration where each element is equal to the sum of Fibo for the previous one and Fibo for the previous one. So it reads quite well. Unfortunately, it's got a few performance issues. The first performance issue is that it's consumed the stacks quite fast. So if you give it a big enough number, which is not huge, but it's just big enough, it's going to overflow the stack. And the reason is because each iteration is calling itself twice. It's kind of generating a tree of stack suspensions for all the iterations. And the other thing is that each iteration is also invoking the same Fibo for the number n many times. So if we start from Fibo of 10, we are executing Fibo 9, 8, 7, and so on. And we do another iteration for Fibo of 8, and we are doing 7, 6, 5, and so on. So it's repeating the same operation many times. So for these 2 reasons, it's really expensive. But there are ways of rewrite the Fibonacci generation function in a different way, and here I have an example. This way it's just making explicit the partial results instead of delegating saving the partial results on the stack for later retrieving them when the stack is unrolling back, and this is making the accumulation of the partial results explicit on the list of arguments, in this case of the arguments of the loop recur. So this version doesn't suffer from stack overflow, is reasonably efficient, and is also returning like very large numbers, as you can see here below. So why am I talking about Fibonacci and iterative recursion compared to non-iterative recursion? Is because reduce is kind of the prototypical iterative recursive process. So when you're using reduce, you are using the mechanism, like the typical mechanism in functional programming of transforming a loop that is non-tail recursive, like the first one that we saw, into a loop that is tail recursive and is making the partial result explicit. Reduce, when you use reduce, you're using, for example, to calculate the Fibonacci numbers, you're using an iterative recursive version that is not consuming the stack. And when you're using reduce in general, this is what happens. So I rewrote the Fibonacci sequence in terms of reduce, and you can see it here. We can see it also in action, and of course it's going to return the same results like 55 or like very large numbers still here. And as you can see here, I had to adapt the Fibonacci sequence a little bit to what reduce requires, which is accepting a function of two arguments. The first argument being the results so far, the partial results, and the second argument being whatever is in the sequence that reducing is targeting, or the collection that is then sequentially iterated by reduce. So this is to explain a little bit why we have reduce and what it represents in functional programming, but in specifically in Clojure, there are a few things to keep in mind in the contract. So it works on sequable collections. So vectors are sequable collections, but there are, sorry for that, there are other collections that are not sequable. Main example is transients. Apart from that, though, all the other collections in Clojure are sequable, and even the like Java collection types, iterable collection types, are handled gracefully by reduce and by the function sec in specific. So unless you're using transient, there won't be any problem, and you can just use it. And we can use that. We can see that if we try reduce on top of a transient, it's just throwing an exception. So in order to understand what happens with the arities, I prepared this debugging function that is a function with many arities that is just printing the arguments. So we can see what happens if I try to call reduce with a few like corner cases and combination. So reduce on nil is going to work, and is going to invoke the zero arity of the reducing function. That means that if you call it reduce plus on nil, that is going to invoke the zero arity of plus, which is the zero number, which is the identity for sum. Same happens if you invoke reduce on an empty collection. In this case, it's still invoking the zero arity function and returning nil. And if instead you can pass an optional initial value for the reducing function, which is the since there is always a pair of arguments that the reducing function will be called with, if an initial value is present in the pair, then the initial value will be sent first to the reducing function along with the first element of the collection. But if there is no element in the collection, like in this case below here, what happens is that none of the arity of the function, of the reducing function, are invoked, and the initial value is returned straight away. So the summary of this discussion about the contract is that most of the time you don't care about having zero arity reducing function, but if you know that your collection might be empty or nil, you are required to use a zero arity function that also supports two arity function as well for the main reducing function. I hope that was clear enough. We are moving to like a one way to use reduce in like a more complicated example, or a more interesting example perhaps. So we have the typical word count here that you may see in also other many languages, and is using a combination of map and reduce, which is not like by coincidence having the same name as the map reduce paradigm, because what we need to do for word count is to associate, like to split this string into words, and then associate the number 1 to each word, and then see if there is the same word twice. We sum up with the previous one, so we accumulate the count for each word. And in order to do that, let's start from the bottom here. We split, the first step is to split the string into multiple pieces, and each piece is a word, and then we count the occurrences of the collection of words up here. And the first thing we do is to create pairs tuples containing the word and the number 1, so very straightforward. And then we ask reduce to go through this mapping of vectors with the number 1 and to accumulate them inside a final map where we are using the word as the key and the count as the value. In order to do that, we use the get function over to the partially accumulating map m, and we search for the key, and when that is not found, we can also provide the initial value 0, so then we can start counting on top of that, and every iteration we assoc into the results map the word, either a new one, either a new key, or a new value incremented by 1 on an already existent word. So if we try that, we can see that it's working fine and is counting the words, and the result is this map where I have an alternating 1 and 2, and if you use it on a very large text you might have higher numbers. And well, what's interesting about this is that if you need this kind of functionality, you're not going to look into customizing your own function to do the word count. There is already a function in the standard library called frequencies, that if you pass a list of words, so you need, well, let me do that first. So I have them, so if you map over this, well, word count will do the trick. So we use word count of the string that I have here. I receive back a collection. Oops, no, this is not what I wanted to do. I just want to use the split function. And let's try again. And we copy the string here. And we've got, I'm missing something, split. Yes. No, it should be okay. It's just returning an array, so in order to see it, we do this. And once we have finally our collection of words, we just pass it to frequencies. So if we do frequencies, sorry for that, frequencies of the previous argument, we can see exactly the same results. So don't think that you need to create your own word count function. There is already frequencies, but there are cases in which you want to customize the way words are counted. Then you can go into a kind of map reduce, like in this case, to make things work. Okie doke. What do we need to know more than reduce? So what we can associate the function reduce with? There is a reduce KV function which is especially dedicated to associative data structures. So if your input collection is associative, so hash map, sometimes vectors, in the sense vectors are associative data structures, but they're not very often used as such. They are more often used as sequential data structures, but if you have that case, you can use reduce KV, and it's taking one additional argument in the reducing function. It's because instead of giving you an item, it's already destructuring that item into a key and a value. So we can see it in action on a map, and is, in this case, is reversing values and keys of the map. There is also another interesting function that is useful for especially debugging reduce, which is called reductions. And reductions is like reduce, like doing the last of reduce. So that would be equivalent to reduce on range 10 with plus, if we take the last. But reductions is showing you each step of the accumulator, so of the ACC local bindings, so the first argument of the reducing function, and it's showing you what happens to that at each iteration, and clearly the last of them is the result of the reduce. Another interesting thing is that reduce knows about a protocol that is created by the reduced function and the reduced question mark function to check for it. And if you invoke reduced at any time during the accumulation, so it could be in between the range of the items in the collection, reduce will stop the accumulation. So we'll stop right there. So essentially you have a way to say, you know what, we reached a specific point in the collection where I know I need to stop, or we can stop. So there's no need to go toward the end and do the entire thing and then return the results. So you can stop reduce by using reduced. You wrap the accumulator with reduced, and reduce will stop. And it works for reduce and reductions as well. A few words about performances. So I have a chart to show you a little bit what is the behavior of reduce against the most common type of collections. And I should tell you first that reduce is implemented in such a way that there is no a single implementation of reduce. There are many implementations of reduce, which is very good for performances, because each collection type can decide by extending a couple of protocols called reduce specifically, called -reduce specifically, can decide to participate in the reducing protocol, and then the reduce function will delegate to the specific provided call reduce implementation to usually because the reducing function has knows about the internal of the specific type and can do specific optimizations. That's mainly the case. And we can see here that the slowest of the benchmark here are the sets, the sorted ones and the normal sets, and that could be maybe explained because set is the is very similar as like an internal implementation. Is very similar to hash maps, where the key and the value are the same. And in order to reduce on them, though, you need to like iterate over the key value pairs. So there is a little bit more work to do, essentially. If we instead go like toward the right of the chart, we can see that the normal range, which is the long range of integers, is the fastest, along with vectors, which has a very fast implementation because it's looking into the internals of the hash trie tree that is the basic implementation of vectors. So overall, reduce is a quite fast operation, so there shouldn't be any trouble in reducing and having the performance of your program still be very good. We're talking here about microseconds, so it's definitely reasonable numbers, and of course is a linear operation, reducing, because it needs to scan over the entirety, over the length of the input collection. Another thing I want to talk about regarding performance is the how reduce behaves in terms of memory occupation. So if you don't do anything, like I can run this reduce function on a very large number here, range of what is that? Is 10 millions or 100 millions, in the order of that, and reduce won't complain about that. The garbage collector will happily garbage collect everything the reduce has already passed over, because after the plus operation happens, the elements of the range can be garbage collected just fine. But if you can also reduce and create not just a scalar, you can reduce and as an output have another collection. So if you don't pay attention, and if, for example, here I'm just grabbing elements from this huge range and moving them into a list with merge, even if I want only the first 10 of them, reduce is not lazy, is going to scan the entire sequence, put the entire sequence inside the list, and very likely, depending on the condition of the JVM how much memory there is available, will result in a GC limit overhead exception. So essentially, the garbage collector cannot collect enough garbage to maintain the memory free and to allocate the second list that is created by the merge. So this is not returning at the moment and is heating up my CPU. So I'm going to try to kill it and show you also another example of holding on the head of the sequence, which is a little bit more subtle to see. So we have again the very large range, the very large list of numbers here. And what we are doing is doing a reduce on that, and that should be fine. We saw it in the first line here. But the problem here is that before that reduce, we are doing another iteration to grab the last of excess. So also last would be fine in other situations. So it would go through the input collection, input sequence in this case, grab each element and by reaching just the last, and everything would be fine, would be garbage collected behind that. But the fact that we have then another reference to the same collection here, the same range down here for the reduce, makes it so this last, once last is finished and returning the last element, everything in the big range cannot be garbage collected because the head needs to be still available for the second operation that happens here, because it cannot be instantiated another time. So also in this case is going to return an out of memory, but it's just less easy to see. So again, depending on the JVM settings and condition of the JVM, it might require some time, less time, more time. So we're not going to wait for that. It's just not returning, which is usually a bad sign. And as well, the fact that the my 4 cores are completely busy doing this operation, meaning that the garbage collection threads are extremely busy trying to garbage collect something that cannot be garbage collected, essentially. So I'll just pause here or try to kill it, but this was the last thing I wanted to show you. So as usual, thanks for listening, thanks for watching the screencast. The show notes and the examples I've just showed you will be available at the GitHub project, the Clojure pills, at my reborg GitHub account. Hope you enjoyed it, and until the next time, goodbye.